These computations will allow you to optimally select the QC rules appropriate for your laboratory. The main problem with them is the time and effort required to do them. In conjunction with Bio-Rad, Dr. Westgard has automated this process with Westgard Advisor. Dr. Westgard's algorithm has the performance characteristics of the most useful QC rule combinations, which can be used as a part of Bio-Rad QC management software. Given inputs of the TEA, bias, and imprecision, his algorithm will calculate S-critical and select the optimum QC rule that has sufficient error detection and the lowest probability of false rejection. Westgard Advisor automates QC design. Using Westgard Advisor is simple. Begin by configuring the quality requirements for each test. Then specify the QC data requirements. Next, Westgard Advisor guides the user through a 4-part wizard. Part 1 asks the user which lot or lots to apply the rules to. Part 2 asks the user to define a date range of data to use in the calculation for determining test performance. Part 3 asks the user to make selections regarding which control levels data to use in the calculation for determining test performance. Finally, the user makes selections regarding the group that they want to be compared to. Westgard Advisor then generates rules based on your selections. To evaluate the impact of QC design in a clinical laboratory, Dr. Westgard performed the computations outlined in this presentation for a laboratory that was using a 1:2S QC rule for all of its general chemistry tests. For the 18 tests considered, it was determined that 14 of them could use a 1:3.5S rule. In general, these tests were working well within their quality specifications. The other 4 tests had more significant issues. A 1:2.5S rule was selected for albumin, a multi-rule for chlorine and CO2, and a special strategy was developed for calcium. One of the most important aspects of QC design is that it clearly identifies which tests perform with no problem and which tests need more care. If our quality specification of creatinine kinase is plus or minus 30%, and our creatinine kinase test performs with a quality of plus minus 2%, we don't need to worry about improving creatinine kinase. We should instead focus on other analytes that are not in such good shape. These changes resulted in a dramatic drop of false rejections in the laboratory, with significant savings due to the savings of retesting. It should also be pointed out that the quality of the problem analytes increased due to the tighter controls that were placed on them. The general impact of quality control design is to increase the scrutiny of tests that are in danger of being out of specification, and to reduce scrutiny of tests that don't. This allows a laboratory to become more efficient while increasing the quality of its testing. This should be the goal of all of us. For all of your laboratory QC needs, go to www.qcnet.com.